Thank you. Thank you for the nice introduction. Right, I should say I'm a postdoc here at Vienna of Volker Branding, who introduced me. And today I will talk about the work that I did during my PhD. So I did my PhD at the University of Münster in Germany under the supervision of Anna Siffert. And well, these things that I'm going to talk about today were the fruits of that. Well, I want to begin my talk by mentioning what I mean by a wormhole, because that's, I guess, what people are mostly interested here. And the definition that I have here originates from Morris and Thorne from 1988. The definition that I have here is essentially equivalent to their definition, although it's a bit differently formulated. So we work with wormholes in the static spherically symmetric setting, which means that we describe them as spacetimes, as manifolds with topology R2 times S2, right? You have the S2 for the spherical symmetry, and then you have one copy of R2 for your time variable and another copy of R for your generalized radius. And we will assume that the metric is given in these coordinates as described here, which maybe you haven't seen such a coordinate system in spherical symmetry yet, because usually in spherical symmetry one likes to use this radius function as a coordinate, which has a geometric interpretation as being your the radius of the spheres that your manifold is foliated by. But here it turns out that for wormholes it's inconvenient to use it as a coordinate, so instead we view it as a dependent variable. Right, and then we want to impose certain conditions on the metric coefficients. So first of all, not so excitingly, we just want them to be smooth, and of course we want this radius function to be positive everywhere. But more excitingly, we want the metric to be asymptotically flat with two ends, which is somehow the main feature of wormholes. You want to have a sort of a connection between two asymptotically flat universes. In this particular coordinates in the static spherically symmetric setting, this essentially means that your radial function should tend to infinity at plus minus infinity. And you also want to impose a certain growth rate for it, which is done by requiring that this quantity here, which is the so-called Misner-Sharp mass, or also the Hawking mass, you want this to have a finite limit at both infinities. And finally, for the temporal coefficient tau, you also want that to tend to some finite limits at infinity. Ideally, you would want this limit to be 0, right? Because you would like the metric to converge to the Minkowski metric, but you have to just assume finiteness. For the wormholes that we will discuss later, we will be able to now go to 0, though. Right, and I should mention that here and throughout the talk, the dot will denote derivative with respect to rho. So everything will essentially depend only on this generalized radius function, generalized radius coordinate. Right, and lastly, and I put this in parentheses because, well, these first two conditions already define a wormhole as a geometric object, but of course we would like to satisfy general relativity in some sense, right? So we would like the metric G to satisfy the Einstein field equations for some accepted matter model. And well, I write accepted here, but when one considers wormholes, one needs to be a bit less strict with what is to be accepted, because you can show that with these two conditions, every wormhole will necessarily violate the so-called null energy condition. So already there you have something spooky going on. Right, and I will talk about the matter model that I consider in a moment. But first, I want to give you a simple example of a wormhole, possibly the simplest example, which is called the Ellis-Bronikov wormhole, where the metric is given as shown here. And well, I should mention that throughout the whole talk, the topology of the manifold will always be R2 times S2, so I will only talk about the metric, right? Right, and well, as you can see here, this is this second line is the way that the Ellis-Bronikov wormhole, the metric of the Ellis-Bronikov wormhole is usually written down. But here I give you also I write it also in the coordinate system that I use, just so you have it for comparison. Right, and a good way of imagining a wormhole somehow is if you freeze the time variable and you freeze one of your spherical angles, then you are left with a two-dimensional surface, right? And in the case of the Ellis-Bronikov wormhole, that would be just what in geometry you call a catenoid, right? Which is the first shape that comes to mind when you sort of think of a wormhole from sci-fi or whatever. And in general, for a general wormhole, this might not be a catenoid, but it might have like little squiggles, right? The radial function might not only have one minimum. You could have more minima, right? Okay, but now onto the matter model that we use. That's what I like to call the haunted Einstein-Yang-Mills theory. It's formulated as a local Lagrangian theory, as you usually do in GR. So first of all, we have the scalar curvature of the metric G, right? We have a Lagrangian that depends on three quantities. The first is the metric G, and then, I mean, if you stop here, this is the usual Einstein-Hilbert functional, which generates the Einstein field equations. If you stop here, they would be in vacuum, of course, but then we keep adding terms. The first is a Yang-Mills term. So omega is a connection on a principal G bundle, and f omega is its curvature form. And okay, I won't go into details about how you define these norms and all that, but this is sort of, at this point, this is what you would call the classical Einstein-Yang-Mills theory, which was well studied in the past. Now for the spooky part that we need for wormholes, we have a phantom field, which is just a scalar field. But the interesting thing is that it has a reversed sign in front of its kinetic term in the Lagrangian, and that's why it's usually called a phantom field, and why I like to call this theory the haunted Einstein-Yang-Mills theory. Whereas for a normal scalar field, you would have a minus here. Right. What is what? Right, so I will come to that in a second. Actually, the matter model for that one would be if you assume that the Yang-Mills connection is flat, so that this term disappears, so you would just have a haunted Einstein theories in some sense. You just have Einstein with a reversed scalar field. Right, but it will come up later as a sort of as a trivial solution of the equations once we write them down. Right, and then what you do, of course, is you integrate this Lagrangian over compact subsets of your spacetime, which is non-compact, so we need to do it over compact subsets and all that. That's more of a technicality. And you vary it with respect to the three quantities that you have here, and then you get the Euler Lagrange equations. So the first of which is then the Einstein field equation with a certain stress energy tensor, right? The second is the Yang-Mills equation, and the third one is then just a wave equation. You could call it the phantom field equation if you want to be specific, but it is just a wave equation. And well, okay, for the Einstein equations, I write it in a trace reversed form, which is of course equivalent. And again, the main thing to note about this theory and compared to your classical theories that you might be familiar with is that the sign of the scalar field term here is reversed, which, yeah, and that's sort of the thing that breaks your null energy condition in the theory. Right, and then the thing that we want to do is we want to manufacture wormhole solutions of these equations. And well, to do that, of course, already in the first slide, I gave you a good ansatz for the manifold and for the metric G, right? We want to consider manifolds with a Lorentzian metric of this form. And then we still need a sort of a good ansatz for the Yang-Mills term and for the phantom field. Well, for the phantom field, it's rather easy. We also just assume that it's static and spherically symmetric, as I will come to in a moment. But for the Yang-Mills term, you can also do something similar as you do here. You can sort of define a notion of spherical symmetry on principal G bundles. And then you can also define a notion of spherical symmetric connections on those bundles. And then there is a well-developed theory of bundles with symmetry and invariant connections on them, which you can use to derive a general ansatz for the connection. And you can, in fact, do that for any gauge group G. In our case, we will work with gauge group SU2, in which case an appropriate ansatz turns out to be this, which, well, I mean, it's not really important what form it has. The important thing for this talk will be to notice that this depends only on one function, W. And well, I should mention that even for if you choose your gauge group to be SU2, this is not the most general ansatz for the connection that you can have, but in some sense, you can do a lot of reduction and show that this is in some sense, the most general interesting one. Everything else doesn't lead to anything spectacular. And well, you can play this game also, I should mention, you can play this game not only for spherical symmetry, you can have other types of symmetries on your manifold, and then you can still get a full classification of connections with symmetry on bundles with symmetry. But yeah. And finally, for the phantom field, as I said, we assume that it's static and spherically symmetric, which just means that it depends only on the generalized radius rho. And then the wave equation for phi is just a second order ODE, for which you can get an explicit solution in some sense, or at least a solution formula, which you can then insert back into your other equations to sort of eliminate phi from the system. And well, it turns out that, I mean, you only, in the other equations, you only have the derivative of phi appearing, so this constant phi 0 is really not important, but this constant pi 0 will come up later. So you should just remember, I wrote it down here on the, so here on the board, I wrote a little cheat sheet with some of the notations that are important. So this pi 0 will appear, and you can interpret this as some sort of a phantom charge, or the charge of your scalar field. Right, but then sort of if we insert this into the other equations as well as these other ansätze, then the equations actually reduce to a system of ODEs, right? We have 3 second order ODEs for W, tau, and R, plus a constraint equation here, in the sense that if this equation is satisfied at one point, then these other 3 equations will apply that it propagates, so it's satisfied everywhere. Right, and well, I'm showing them to you here just so you see the equations that we deal with. Again, the exact form of the equations will not be important. I will not go so much into the technical details. I will just sort of give a sketch of the argument somehow. But there are a few important things to note here. First of all is that the equations have a sort of an inbuilt singularity in them, in the sense that if R tends to 0, then blow up. So R tends to 0 is a singularity of the equations, and then we will see later that in fact this is in some sense the only type of blow up that the solutions of the equation can have. Secondly, you can see that the phantom field, which I told you, I mean, you can spot where the phantom field appears by just looking at where pi 0 appears, and you can see that this only appears here in the last equation, which is the constraint equation. And well, if you set pi 0 to be equal to 0, then the phantom field does not have an effect on the theory. I mean, you can see that already in the Lagrangian, because the term then disappears. And then you get the classical Einstein-Yang-Mills system for SU2, which was rather well studied in the 90s, and a lot of the results that people were able to obtain are sort of analogs of what I'm going to show you today. And then at that point you might think, okay, well, this seems like a rather small change, especially because it only comes up in the constraint. But actually, if you start looking into the analysis of the equations, the way that this term usually comes in is that, I mean, usually it comes in with the wrong sign or anything, so you lose a lot of monotonicity properties and like that, which basically destroys the analysis and makes things harder in general. And I mean, another thing, you could be tempted to consider this as a perturbation of your equations, right? But the problem is that this term is not going to be large in general. It will decay asymptotically, but that's really a trivial fact a priori. And the final thing I want to notice about the equations is that they have a reflection symmetry, in the sense that it's same if you solve them forward or backward, which you can see because the derivatives always come in pairs. You always either have a second derivative, or if you have first derivatives, then they always come in pairs. So the minuses you would get from a reflection cancel out. So in some sense, it's enough to study the equations forward in rho. Right, and then you can immediately spot 2 trivial solutions to the equations, or at least if you only focus on the Yang-Mills equation for now, you can see immediately that if W is either constantly equal to plus minus 1 or constantly equal to 0, then this one is automatically solved. And then it turns out that the other equations also can be solved explicitly. So in the first case, when W is plus equals 1, then you just get the Ellis-Bronikov wormhole, as I mentioned before, because in this case, it turns out that the connection is flat. So the Yang-Mills term completely disappears in the Lagrangian, and you're just dealing with the haunted Einstein theory. And in the second case, well, I mean, here the solution is a bit more complicated, but again, the formulas are not so important. I just wanted to show you that they're explicit. So in the second case, you get what I like to call the abelian wormhole, because in this case, the connection is U1 valued. So your Yang-Mills theory degenerates to a Maxwell theory in some sense. So if you will, I mean, if you think in comparison to black holes, you could view these family of wormholes as an analog of the Reissner-Nordström family, and that's why you also have this additional condition, just like in the Reissner-Nordström family. And the Ellis-Bronikov wormhole you could view as a sort of analog of Schwarzschild. And in fact, if you remove the phantom field, so if you assume that pi 0 is equal to 0, then if you go back, then if you assume that this is 0, then, well, your Yang-Mills equation will still be satisfied by plus minus 1 and 0. And in those cases, you do get the Schwarzschild solution. And right, and then my main result is that there are infinitely many more of them. So explicitly, so for each R0, you get a sequence of symmetric wormholes. And here by symmetric, I mean that they have a reflection symmetry in the sense, so if you think in terms of your metric coefficients should be even functions of rho, so that the geometry of the wormhole looks the same on both sides. And here R0 would then be the initial radius, or the radius of the spheres at the center of this reflection symmetry. And okay, this sequence is then labeled by the number of zeros of your Yang-Mills potential Wn, and this Wn is then either even or odd, depending on whether n is even or odd. And furthermore, you can also show that the absolute value of W tends to 1 for each n. So here I take the limit in the rho directions, not in n. Right, and I should mention that these solutions are, I mean, I didn't cook them up out of nowhere. They were actually numerically discovered in 2014 by physicists. But they only sort of performed a numerical analysis of the equations and then demonstrated that they should exist. Whereas I did a proof, as I'm going to show you. And more interestingly, I mean, so these solutions were not so surprising, because if you compare to the SU2 Einstein-Yang-Mills theory, the classical one without the phantom field, in that theory you also get a sequence of such solutions, but they don't describe black holes and not wormholes. And this was, I mean, sort of these solutions were found first numerically and then proven to exist in the 90s by a lot of names, some of which I've listed here. So it was very much a collective effort. So I think Bison was the first one who found them numerically, and then Smoller, Wasserman, and Yao, in a series of papers, first managed to show the existence of such a sequence, and then Breiten, Lohner, Forgash, and Meissen managed to also provide a more complete description of the solutions of the equations later. And for us, yeah, I should just mention these last three names are going to be important for us later, so I will usually abbreviate these three names to BFM, just so I don't butcher the pronunciation of the names all the time. Right. Okay, these ones you might not find so surprising, because you saw that the equations are similar, and despite all of these technical issues, you can sort of expect that the solutions might have a similar structure. But what's maybe more surprising and impressive is that these types of solutions, where you have a sequence of solutions depending or labeled by the number of zeros or certain variables, also appear in the study of harmonic maps between Riemannian manifolds. This was done for harmonic maps between spheres by Bison and Schmey, and somewhat more recently by Volker Branding, who introduced me, and Anna Siffert, who was my PhD supervisor. So they also did it for harmonic maps between ellipsoids and also p-harmonic maps between spheres. It would seem that this sort of behavior, where you have sequences of solutions labeled by the number of zeros, really appears in a lot of geometric problems. So here I'll only list two, but I mean, the list goes on. There are more. Right. And now I would like to tell you a few words about the proof. Again, because this appears everywhere, so maybe actually we'll find something useful in knowing how the proof is performed, because the techniques for proving these types of things always have a very similar idea. It's just the technical details are usually a bit different. So of course, we're dealing with a system of ODEs, so we would like to formulate this somehow as an initial boundary value problem. So first of all, I mean, we have a freedom to choose our initial condition, sort of to choose our initial point and the initial conditions in a sort of in a good way, so that we have a nice framework for trying to find the solutions, because we're only looking for solutions of a certain type. So first of all, you'll remember that the main distinguishing feature of a wormhole was that it has two asymptotically flat ends. So your variable r will necessarily tend to infinity at plus minus infinity. So that means that somewhere in between, in the middle, it will have to have a stationary point. In particular, it will have to have a minimum somewhere, but we will only assume that it has a stationary point because, well, we will also deal with initial conditions where it's not necessarily a minimum. So it makes sense to sort of, well, first of all, without loss of generality, we can assume that our initial point is 0 because the system is autonomous. And secondly, we can assume that r dot, the derivative of r is 0 at 0. Then for the value of the radius, we have to just assume that it's positive, but otherwise it can be arbitrary. And then for the temporal coefficient of the metric, we are not as constrained in some sense. So here we could actually take the derivative of tau to be arbitrary at 0, but it turns out that the analysis gets much simpler if you also assume it to be 0. And again, here we allow ourselves to do that because we're just looking for solutions of a certain type. And in the end, as I mentioned in the theorem, we're going to look for solutions that are symmetric anyway. So that means that r and tau should be even functions of rho. So this condition in that case is also necessary. The value of tau at 0, tau itself at 0, is a bit more free. And here I write free instead of writing it as a parameter. Which, I mean, I will explain this in a moment, but somehow this, the value of tau is somehow less important than the values of the other variables. And for now, for the Yang-Mills potential, we also allow arbitrary values, but we have to remember that we still have a constraint equation that we need to satisfy, right? And if you plug in these conditions into the constraint equation, you see something like this. So here's what I mean by the freedom of tau is by the freedom of tau at 0. So you can see here that there is an interaction between tau 0 and pi 0, and pi 0 is an arbitrary parameter somehow. So we can always adjust if we want to wiggle tau 0, we can also wiggle pi 0, and in such a way that the constraint works out in some sense. But we also have to make the observation that this quantity now here needs to be necessarily non-negative, right? Because this is non-negative. And this quantity will turn out to be very important. I will call this the initial energy throughout the talk. I also wrote it here on the board in case you forget, right? E0. So here, I mean, I call it the energy because for me, it's an energy in a more Lyapunov sense. It's a sort of like a weak Lyapunov function of the ODE system, but it's not an energy in the what one would call an energy in a PDE sense. So one should just that. But it's sort of standard to call this the initial energy, even in the older papers related to Einstein-Yang-Mills. Right. Then sort of that's it. We only really need to assume that R0 is positive. So we have three parameters now. We have R0, we have W0 and U0, which we will from now on call the initial data. And we have the set of admissible initial data, which is denoted by scry, big scry 0, which I also wrote here, even though it looks a bit more like a J, but I don't really know how to write scry on the board. And well, we need to assume, of course, that R0 is positive. We need to assume that the initial energy is non-negative. And here we also add a more technical assumption that W0 should stay between -1 and 1. And we can't really make this without loss of generality, but in some sense you can show that the solutions which start outside of the strip between -1 and 1 are not really interesting. So they're not the solutions that we're looking for. So somehow it's also, we're not losing anything by excluding them from the start. Right, and then, well, the goal is basically to determine these three parameters in such a way that the solution is global and asymptotically flat with two ends. as I mentioned before, we have this reflection symmetry of the equations, and we are looking for the symmetric solutions anyway. And then you can notice that if you assume that that u0, which is then the derivative of zero, the derivative of w at 0 is 0, then all three functions are even. Whereas if w0 is 0, then r and tau are still even, but w becomes an odd function of the equations. In particular, I mean, in particular, it suffices to study the problem only for forward in ρ. And as I mentioned before, this is sort of a more general fact. You don't really need to assume that one of them is 0, but then you don't get sort of this nice symmetry of the quantities. You get some sort of a reflection law depending on the chosen initial conditions. But in some sense, you can always, it does suffice to always study the problem only forward in ρ. Okay, and then how do we manufacture our solutions? Well, we use a so-called shooting method. And well, here I mentioned these three guys, BFM again, because the method that we use is the method that they used to sort of study the classical Einstein-Yang-Mills system. Right, what did I want to say here? This basically relies on three ingredients. So you have the so-called classification theorem, which tells you that there's only a handful of types of solutions that you can do the equations, which is already quite impressive. Because, I mean, if you remember the equations, it's quite a heavily coupled system of equations. So just the fact that you're able to classify all the solutions into only a few types is rather nice. Then you have a neighborhood theorem, which you can view as a sort of stability result, in the sense that if you have one of the solution types from the classification theorem and you wiggle the corresponding initial data a little bit, then you want to know what kind of type those solutions can have. And then finally, we have the energy theorem, which essentially will tell us how the solutions with very small initial energy or very large initial energy behave, or rather which class they fall into. And then with those three ingredients, after you have them, you can shoot. And here, I mean, it's called a shooting method. I guess historically the reason is because if you think you're shooting a cannon or something at a certain velocity, right, and then you see that you're overshooting your target, then you know you need to take a smaller velocity. And then somehow the idea is to take the infimum over all the velocities that overshoot the target, and then you hope that you're going to land exactly at the target. And this is sort of similar here. I will sketch this argument now. Well, if you are familiar, I should just mention, if you're familiar with the work of BFM for the classical Einstein-Yang-Mills system, you're gonna probably recognize the classification theorem and the neighborhood theorem as being sort of the statements. The statements are basically the same as in the classical Einstein-Yang-Mills theorem, which is quite. I mean, it was quite extraordinary to me because, as I told you, the analysis gets quite messed up and all that, and I was expecting to get a lot of different behaviors, but then it turned out that the classification theorem and the neighborhood theorem are preserved. So in some sense, the system is, the Einstein-Yang-Mills system is very rigid, even under, I mean, if you consider the phantom field as a large perturbation, the Einstein-Yang-Mills system still remains rigid. So, I mean, of course, a lot of credit goes also to these three guys, even though I should also mention that I do have some problems with certain arguments that they do, and I don't really agree with them. But I did find alternative ways of doing things that are arguably also simpler. Right, but that all being said, first I want to tell you about the classification theorem. So basically, it tells you that if you look at your equations and you start with initial data in I0, then your solution can fall into three categories, the first of which is the singular category, which are solutions for which R tends to 0 at finite ρ. And I told you when I showed you the equations that, I mean, this sort of R tending to 0 is somehow a singularity that's already built into the equations. And well, it's kind of interesting here that this is the theorem tells you that this is the only thing that can happen if you have finite law. Whereas you might expect that, I don't know, maybe R stays bounded away from 0, but W dot explodes or something, but none of these things can happen. Second, well, and so these are the only orbits for which the solution stops existing at finite time. The second and the third are global. So first we have the asymptotically cylindrical orbits, which are global, for which R tends to 1 at infinity and W has infinitely many zeros. So here I call them asymptotically cylindrical because, again, if you remember the metric, when R tends to 0, then the metric of the spatial part tends to the metric of a cylinder with a spherical basis. And lastly, we have the asymptotically flat orbits, which are again global. R tends to infinity, and you also have this condition on the mass that I had on the first slide, but I didn't include it here just for brevity. And then you either have W identically equal to 0, so that your solution is one of the trivial solutions, trivial abelian solutions that I showed you before, or you have W tending to 1 in absolute value. And these are all. So this basically tells you these are all possible types of solutions that you can have, which, I mean, I don't know, to me this was rather funny. And now what we're going to do now is we're going to start, instead of working with the solutions themselves, we're going to start working on the set of initial data. I mean, this sort of classification theorem allows us to partition the set of initial data into different types, into different subsets, right? Because now we have only feasibly few that we can sort of write down. But it is beneficial to actually refine this partition a little bit rather than using this singular asymptotically cylindrical and asymptotically flat. So we're going to define the following subsets of the initial data. So first we have the crashing orbits. And well, I should just mention that I wrote down all 4 of them here for later reference if you're going to need them. So first we have the crashing ones, which have R tending to 0, but W stays in the strip between -1 and 1. And these are the really badly crashing ones. If you're familiar, for example, with the works of Smoller and Wasserman, they also call them crashing. And well, these are the types of solutions that you really want to avoid at all costs. Then you have the escaping ones, denoted by E. And well, here we have an additional parameter N. So these are also singular in the sense that R tends to 0, but they exit, but W exits the strip, and W also has N zeros. So actually, you can show that if W ever exits the strip, then it will stay outside of the strip, and you will in fact have R tending to 0. So somehow we could even delete this condition. We could just assume that that W exits the strip and has N zeros, and call them escaping. So these are somehow less bad than the crashing ones. And we have the O, the oscillatory ones, which are global and W tends to 0. So these ones can either fall into the asymptotically cylindrical category, or they can also be asymptotically flat, but identically 0. And well, the reason for calling these ones oscillatory will be clear in a moment, I think, even though these ones can also be just identically 0, right? And finally, we have the regular orbits, which are the ones that we are looking for. So these ones are also global. So these ones fall into the asymptotically flat category, but with W tending to 1. Well, here, in addition, we also want to count the number of zeros of W. But again, so I will talk about these 4 types of sets now, but so if you ever forget what they are, you can find them on the blackboard. Well, now with this at hand, I can give you a sketch of the proof by literally drawing a sketch of the set of admissible initial data here. I will only do the odd case because the even case is very similar. So here by the odd case, I mean I'm assuming that W0 is equal to 0. So then we only have 2 parameters. We have R0 and U0. You'll remember we had to assume that R0 is positive. And well, for U0, you can actually assume that it's non-negative without loss of generality because of asymmetry in the equations. The equations are also reflection symmetric in W. And then you remember we also, for the set of admissible initial data, we had this additional condition that the initial energy should be non-negative. And here I draw the region where it is negative. So this is the region that we don't care about somehow. We only really want to see what happens in this part of the set. And now the idea is that each point here will belong to one of these 4 sets from the partition that we have. And the idea is to draw sort of what this set now looks like, where each set is located. So first of all, you can immediately say that that this sort of line here, this ray here, is in O, the oscillatory orbits, because, well, W0 is equal to 0, and nu0 is also equal to 0 here, so that the solution is trivially identically equal to 0, or rather W for the solution is identically equal to 0, so automatically it goes to 0, and I have a typo here, sorry. There should be a 1. So I mean, in particular, these are identically, W is identically 0, so it tends to 0, and they are global, as I showed you before, because you have an explicit formula for them. So these ones belong to O, the oscillatory orbits. Then we have the first part of the energy theorem, which I like to call the low energy theorem, because here we're assuming that the initial energy is equal to 0, and then you can show by an analysis of the initial conditions that either your solution is in C, so that it crashes with R0 less than 1. So this tells us that this thick line here is in C, or it has to be this fixed point here, which is 1, 0, 0, which we already know is in O by the explicitness of the solution. Even though I should mention this one is not asymptotically flat. So this one, only this one here is asymptotically cylindrical, and then as soon as you assume that R0 is greater than 1, you get into the asymptotically flat ones. But they are all in O, nevertheless. This is sort of like a lower bound for our shooting method. Then we have the high energy theorem, which tells you something when the initial energy is large. So here we have to fix R0, and then if the energy is sufficiently large, then W will escape the strip monotonically, or in other words, if we go high enough up here. So if you look at the formula for the initial energy, we're assuming that W0 is equal to 0, and well, R0 is fixed. So somehow taking the initial energy large is the same as taking U0 large. So if we go far enough up, we will be in E0. So well, scry E0. Right, and this theorem is, I would say, the main difference between the classical Einstein-Yang-Mills theory and the haunted Einstein-Yang-Mills theory, because first of all, for the classical Einstein-Yang-Mills theory, the odd case that we're considering here was not really interesting because it's in some sense singular, so it's not really well posed. But here we can consider it, and again, I would say that this is the sort of the main difference, and it's surprisingly annoying to prove. I mean, if you think what we're trying to say here is that if we choose the initial velocity of W large enough, then W will escape the strip monotonically, which somehow seems intuitive, but the problem is that we have the coupling to the other variables, and this coupling really messes things up. I mean, first of all, you could have situations where W, if I sketch, if you think of your dependent variables, so your W could start increasing very fast, right? If we put one here, your W could start increasing very fast, but at the same time, R, starting from R0, could just drop down to 0 very fast as well, even faster. So maybe W doesn't have time to really escape, and in that case, we would be in C rather than in E0, and that completely destroys the argument. Or even worse, if you look at the equations, you can sort of see that the dependence on the other variables also tells you that you could have W increase. I mean, it could start increasing very fast, but then the derivative of W then also decreases very fast, and then it could decrease faster than W exits. So I mean, you could also have like a very sharp increase and then suddenly a decrease, and then you would stay in the strip, and this is also somehow bad for the shooting method. Right, but so these last two theorems are then the energy theorem, and then finally we have this neighborhood theorem, which, as I told you, gives you sort of a stability result somehow. And first of all, you can see that the sets of the singular orbits C and En are open. So first of all, we can conclude that we can conclude that there is a, because this thick line is in C, we can conclude there is a small neighborhood of it here that's also in C. And in particular, we also know that this guy is open, so we somehow know that these guys can't intersect here, they can't even touch. But we still don't know what happens for R0 greater than 1. And here the second part is that the initial data close to oscillatory orbits has as many zeros of W as we like, and that's the reason for calling them oscillatory or oscillating. So what this means is if I take an orbit here, then I can always, if I take an orbit here and pick an integer, I can always find a sufficiently small neighborhood so that all of my orbits have at least that many zeros of W. So this tells us that in particular that this guy also can't touch O here, right? So there is certainly going to be some separation of it because our number of zeros is fixed to be 0 here. So there's certainly going to be some separation here. And already here, then we can conclude that this bound, if you think of the boundary of E0, or if you prefer to think in terms of infimi, but as I did before with the canon, you can fix R0, and then then you know that high enough you're going to be in E0, and then you could try to take the infimum over E0 and hope that you land in something good. And already here that you can conclude that you land in something good because by the classification theorem, the only possibility for this line is that it's in some Rn. In one of the regular orbits, right? I mean, for sure we can't be in C or any of the ENs because these are all open. In particular, we also can't be in E0 because then that would contradict the definition of the infimum. And we can't be in O because that would require us to go through arbitrarily many zeros of W. And then sort of by exhaustion, you already, and by the classification theorem, you know that you need to be in one of the Rns. But the question is which one, and I mean, you expect it to be R0, of course, but you need to show that, and I mean, sort of the final piece of the puzzle then is to show that if you wiggle regular initial data with n zeros, then you're either still in Rn, or you're going to be an escaping orbit with the same number of zeros or one more. But the point is you can't lose any zeros. So in particular, the only possibility then that remains for this curve here is that it's contained in R0. And that's already a great success because now we already manufactured our solution of a wormhole solution of the equations. But now, I mean, we would like to continue this inductively, of course. Ideally, now we would like to conclude sort of that if we keep going down, that we're going to be in E1 now. But here one needs to be careful because, I mean, if you look at this last part of the theorem, it only tells you that, well, we could still be in E0 again here, or we could still be in R0, or we could be in E1. But then the way to avoid this is instead of taking your infimum only over E0, you take it over E0 in union with R0. Then you're going to know for sure that you land, I mean, you're still going to land in R0 by the same argument as before. And you're going to for sure know that you can't have less than 1 0 anymore because you already took the infimum over that. So then if you do that, you are going to be in E1, and then you can play the same game inductively, right? Then you can take your infimum over E1 in union with R1. That's going to land you in R1, and so forth and so forth. You can sort of get a solution which is asymptotically flat, regular, global, and has n zeros of W. And somehow with this technique, you also for free you get this sort of oscillatory orbits here, so you can show that for R0 less than 1 there exist non-trivial oscillating orbits, which is not really interesting from a wormhole perspective, but it's interesting from an ODE perspective, maybe. Right. And then for the even case, I mean, I just show you the picture. It's basically the same thing. The only difference is that here you have these trivial solutions, which represent the Ellis-Bronikov family. So in some sense, you don't need the high energy theorem as your sort of upper bound for the shooting method. You can use this solution to start with your shooting method, and then you can basically perform the same argument. And again, if you're familiar with the classical Einstein-Yang-Mills theory and black holes, this is the picture that you usually see there as well, sort of something that looks like this. So qualitatively, it's very similar. Right, and then, well, that basically then completes the proof of the theorem, but then I want to just say a few words for continuations of this work. First of all, we only considered here symmetric wormholes. In particular, we assumed always that either W0 or U0 is equal to 0, but this seems to be unnecessary. In fact, it seems that you can show that there exist also asymmetric solutions where neither of the initial conditions is 0. But that becomes a sort of a harder problem, because then you need to know a good way of connecting your forward orbits to the backward orbits. And as I told you, there is a sort of a reflection law for it, but it's not immediately clear how to do it, because for the solutions that we constructed here, we already had symmetry, so we already knew that once we construct an orbit that extends sort of in the correct way all the way to infinity, then by reflection it's going to do the same thing backwards also. But yeah, I'm almost done. But for the asymmetric ones, this is not so clear. And well, okay, my other points are not so important, so I think I will just stop here.